All right, this evening's presentation is Piecing Together Earth's Puzzle. We'll be talking about plate tectonics, volcanoes, and the flood. This is the second presentation in our flood geology, creation geology series we've been doing here at Missouri Association for Creation. And we are building up to talk about Mount St. Helens and some of the interesting things we can learn from those eruptions in the 1980s. Last month or last meeting, we talked a lot about this word uniformitarianism. The present is the key to the past. And we talked about this ideology that is very much prevalent in all of the sciences, but especially in geology, that we should explain what happened in the past by reference to processes we observe happening today. The present is the key to the past. And this naturally means, since present processes, for the most part, are not particularly rapid, with exceptions, most things seem to happen gradually these days, especially when we're talking about geology, the surface of the earth, and so forth. And so it's then logical to say that most geologic features would form gradually over millions of years. This idea of uniformitarianism, as we learned last time, was really popularized, systematized, advocated by two English men in the late 1700s, early 1800s, James Hutton and Charles Lyell. Both of these men advanced the idea of deep time, of vast ages of time, to essentially replace the Bible's chronology. And both of these men were very much ideologues. And I don't mean that in a pejorative, a negative way. It's just, it's a historical fact. They had a very strong sense of how the world ought to work. And they really wanted to describe Earth history in terms of gradualism and cyclical change, things that repeat over the ages. And they argued that presently observed processes were the only processes that should be used to explain the history of the Earth and the history of geology. And of course, they rejected the biblical flood. Charles Darwin was especially influenced by these men, in particular Charles Lyell. And in fact, Charles Darwin made a lot of geologic observations on his voyage on the Beagle. We talked about the Santa Cruz River and his statement of the seeming lack of power by the river, and yet in the lapse of ages, it could do an incredible amount of work, of erosion and so forth. And this idea of gradualism and small little changes over a long period of time doing incredible things is obviously very interesting to a man like Darwin, and it played a big role in the development of his evolutionary theory. And we talked a lot about Stephen Jay Gould, one of perhaps my favorite evolutionists, because he's a very honest, he was a very honest man, a very honest philosopher, scientist. And even he recognized that uniformitarianism and this commitment to gradualism was actually an impediment. It was actually causing geologists in his day, and I would argue even today, to miss things about the rock record and the fossil record because they were so committed to seeing gradualism. And we have Charles Lyell and James Hutton to thank for that. Of course, uniformitarianism runs directly counter to Scripture. 2 Peter 3, verses 3 through 7. In that passage, Peter speaks of those who are willingly ignorant. They willfully forget the Bible's account of creation and of the biblical flood, because both of those events involve processes that don't happen today, never have happened today, and are completely unlike what we see happening in the present. According to the Bible, the present cannot be the key to the past. Revelation, rather, will be the key to the past, what God has revealed to us in his word about what happened. And so we contrast these ideas of uniformitarianism in geology versus catastrophism. The biblical record, the Bible's history, is clearly a catastrophist one. Now, catastrophist does not mean creation, doesn't mean the Bible's history. There are other kinds of catastrophists out there who believe in other versions of Earth history, but the biblical version is clearly a catastrophist one. So with that being said, let's ask a very important question. Why do we have oceans in the world today? Obviously, the Earth's oceans cover the majority of the Earth's surface. In fact, 70% of the Earth's surface is ocean. And we might take that for granted. It seems like oceans have always been there, and they're there because that's where they belong. But if you remove the water from the oceans, it should become pretty obvious that it's not just the water that makes an ocean. There's actually something very interesting and very different about the surface of the Earth under the ocean versus the surface of the Earth on the continents that we all inhabit. And this goes to the structure of the Earth. So the Earth is not simply a round rock in space. It's a much more complicated and dynamic system than that. In fact, the Earth is composed of several layers, like layers of an onion that make up its internal structure. The three primary layers for now we'll look at are the crust. This is the rocky surfaces that we walk on. It's the rocky seafloor beneath the oceans, and it's actually an incredibly thin layer, really imperceptible at the scale we're looking at in this picture. The bulk of the Earth's volume is made up of the mantle, and then beneath the mantle is the core of the Earth. The core is also subdivided. There's an inner core and an outer core, and it's essentially an iron nickel composition. We know this through various means, primarily through seismographs and through seismology, rather. And then the mantle of the Earth is the part that interacts the most with the crust. We really aren't affected other than through things like the magnetic field. We don't really deal with the core, and we don't deal with the mantle except indirectly and through instances where the hot material in the mantle interacts with the crust and forms things like volcanoes. So the mantle is not molten, but it is very hot, and it is plastic. It is deformable. And so it does behave in a sense like a very thick fluid type medium. Let's look at this little pie chart here. We can see a little more of the subdivisions. Of course, we have the inner and outer core there in the gray and white, then the mantle, and the mantle itself is subdivided into various units as well. The asthenosphere and the lithosphere refers to the crust, if you see that on these charts. So we're interested in the crust right now. That's the part that we actually deal with, right? And so there's actually some interesting differences between the crust that makes up the land masses, the continents, and that of the oceans. Continental crust is on average of a granite composition. The basement rock of the continents is pretty much granite or some related rock. There's sedimentary rocks on top of that. There's soil, there's trees, there's people, but the bulk of the continents is made up of granite. The continents have an average density of about 2.7 grams to cubic centimeter. You don't need to remember that particular number, but it's going to be useful for comparison in a moment. On average, the continents are about 20 miles thick. There's quite a bit of variability. And of course, when we say the thickness of the crust, you have to factor in the tallest mountain, right? Because that's represented as crust. That's crust rock. And mountains themselves have massive roots, just like an iceberg floats with just a little bit poking above the surface with a large body beneath it. Mountains work in a similar fashion. Ocean crust, primarily composed of basalt. We'll talk about basalt later on, but it's a lava rock. There's very little sedimentary rock in the oceans, and the average density of this basaltic ocean crust is about 3 grams per cubic centimeter. So it's a little bit denser. That's important. Hold on to that. Average thickness of the ocean crust is around 4 miles. Again, it's variable, and we'll talk about that a little bit later on. So if we compare then continental crust and oceanic crust side by side, we see obviously the continental crust is quite a bit thicker, but it's also a less dense rock, and ergo it's, believe it or not, lighter than the oceanic crust, again, for its volume. And this means that oceanic crust tends to float, tends to ride a little bit lower on the surface of the mantle as opposed to the continental crust. And this difference of density means that the oceanic crust is naturally going to sink and relative to the continents, and it forms the ocean basins. And of course, those ocean basins are where the oceans live, and we're all very grateful for that. That's why we have land masses that are above the water, and the oceans, for the most part, stay where they belong in these oceanic basins that are formed by oceanic crust, which is denser. So these ocean basins, we can see this this chart here. Notice that the continents don't necessarily end at the shoreline. Most of the continents actually extend out a little ways, and you have a continental shelf with shallow ocean water, and then there will be a drop off where the continents and the edge, the borders of the continent comes to an end, and you usually have a fairly steep drop off into the abyssal plain, and that is the interchange between our continents, our continental crust, and our oceanic crust. So that's some good background. Remember that the ocean basins and the continents are both sort of floating. You can think of that. And that already is a hint, right? That these might not be quite as fixed and static as we like to think about them. Now, we look at the continents themselves. We're struck right away by their shapes. They're kind of seemingly random, and yet they kind of also resemble jigsaw puzzle pieces. We can already, just looking at this view over the Atlantic, we can see some possible shapes that maybe would go together. And it's not very hard to come up with a configuration where they do fit together. And people have noticed this for a long time, hundreds of years, in fact. Throughout history, people have speculated if maybe these continents might have been part of one continent at some point and maybe have broken apart and moved to their present locations. Of course, that seems unlikely. The continents don't seem to move day to day. But nonetheless, this shape is certainly very interesting. But it's not just the shapes of the continents that give us this idea. It turns out that there's a lot of features that we can find in different different fields of science even that seem to connect these continents back to each other. For example, there are mountains in the northeastern United States that seem to have twins, matching mountains, matching mountain chains, in fact, in northwestern Europe. The same phenomenon between South America and Africa. Coal beds in the eastern United States correspond very well with coal beds in Europe. And then we find fossil plants that seem to link many of these continents back together, and fossil animals as well. And there's many more examples that we could talk about here, mineral deposits and so forth. Again, these are features that the continents seem to have in common, but this is important. You do not find those features in the ocean basins. Those mountain chains are missing in the ocean. Those fossils are completely absent in the ocean. And so the connection would require, if there is a connection, that those continents were once directly adjacent to each other in order for example, this coal seam to actually have a connection to the coal seam in Europe. So these and other pieces of evidence suggest that the continents may well have moved apart at some time in the past. And the Bible actually seems to give hints of this as well. Genesis chapter 1, verse 9, in the creation account, this is day 3 of creation week, God says, "Let the waters below the heavens be gathered into one place, and let the dry land appear." Now, this suggests that there was only one ocean and one continent at the end of creation week. That's not necessarily indisputable, but it certainly suggests that. And so this idea of continental breakup, that the continents that we now have are actually pieces of one larger continent, has been around for quite some time. In fact, this man, Antonio Snider Pellegrini, was a Bible believer. He was a French geographer, and he wrote a book, The Creation and Its Mysteries Unveiled. I won't try the French title. This book was very important in that it was one of the first cases where someone actually made the case for a supercontinent that broke up and that the continents moved apart to their current locations. And most interestingly, Antonio Snider Pellegrini placed this continental breakup during the Genesis flood. Now, Antonio Snider had some other ideas that weren't necessarily quite as profound, but nonetheless, this particular one is very interesting. And if you can think back, what else happened in 1859 that might have stolen the thunder from Antonio Snider Pellegrini? Well, of course, it was the publication of Charles Darwin's Origin of Species by Means of Natural Selection. Charles Darwin's book was a lot more popular, it turns out, than Snider Pellegrini's attempt at fitting geology into biblical history. That was not so popular. People were looking to move away from the Bible as a source of historical information about the history of the Earth. And Darwin was definitely the one to go with in 1859. And so Antonio Snider Pellegrini's work largely went unrecognized. And it is in fact this man, Alfred Wegener, who was a meteorologist in Germany. It was left to him to sort of rediscover this idea, although he was not interested in fitting this into a biblical time scale. In fact, his theory came to be known as continental drift, the origin of continents and oceans, the English title of his most important book in 1915. And Wegener and other scientists at the time were very much convinced by the fossil record, the shared fossil records between the continents that we've mentioned earlier, as well as other lines of evidence. And I'm skipping over a lot of history here. There were some very important discoveries, especially when it comes to the geomagnetism of the Earth, the orientation of magnetic minerals that tell us where continents were in relation to the magnetic poles. Lots of very important discoveries that happened that pretty much clinched for most geologists that plate tectonics and continental drift in some form were the best explanation for the Earth's geology. And so that brings us to the theory of plate tectonics. Now, how does this theory work? So we're going to just summarize the current conventional form of plate tectonics here. This is not no creation stuff here just yet. The basic premise is that the Earth's crust is formed of tectonic plates. These plates include both the continents as well as the oceans. All of the Earth's crusts exists as part of a plate. These plates then float, if I can use that term a little bit loosely, on the mantle, and they can move relative to each other. And in fact, they can even interact with the mantle itself. The plates interact with each other along various types of faults. So, for example, you could have convergent faults where plates are coming together. You could have divergent faults where plates are pulling apart. So they're diverging from each other. And then you can have transform faults and other types of faults where plates are moving perpendicular to each other and so forth. And so this interaction is then what drives volcanoes and earthquakes. We find these at the plate boundaries, so the edges of plates. In the interior of plates, things are mostly pretty stable. It's the edges of the plates where stuff gets really interesting. So the continental plates we can see here in this map. Notice the big yellow plate there marking the Pacific, very important one. Then we have the tan North American plate. You can see how it's not exactly the shape of the continents, but you can see the general shape there. It reflects the continental geography as well. Notice also the South American and African plates and how they have that same sort of curvature. So continental plates then lead to continental drift. These plates can move with respect to each other. And so in this reconstruction here, we can see that around 225 million years ago, supposedly, we have the Pangaea supercontinent. And you can see the basic outlines of our continents today, but they are put together in a different configuration. Then over the course of the next 100 million years, Pangaea breaks apart, and we have slightly smaller supercontinents, still bigger than today, but broken apart from Pangaea. And that continues until the last 100 million years ago, where the present continents are supposed to have separated and finally moved to the locations where we find them today. Here's a little animation that is helpful in visualizing this process. Notice how the continents, they don't all move in the same direction. I'll play that one again for you. There's actually a lot of factors in determining which way a plate is going to go, how fast it's going to go, what it does as it interacts with other plates. And so this is a very complicated process, but we're going to break it down to just a few simple processes that are important. So when continents and plates move, this leads to something called continental collision, which is a very important process in plate tectonics. So again, we're going to zoom in now and look at the collision of India with Asia. This was a particularly important collision because it's the collision that forms the Himalayan mountains. And so we see India crashing into the southern border of Asia, crumpling Asia as it does so, just like wrinkles in a rug, just smashing it together. Some material is diving beneath into the mantle, diving beneath Asia. We'll talk about that in a moment. But this crumpling and folding is what produces the tallest mountains in the world, the Himalayan mountains. Mount Everest here in the picture, the Himalayas, some of the Earth's tallest mountains. The rock on the top of the Himalayan mountains, for the most part, is marine rock. It's rock that was underwater, in many cases may have been ocean floor, and it is now many thousands of feet in the sky because of continental collision. Continental collision also gives us the Alps and the Alpine mountain chains, which dominate Europe. It gives us the Atlas Mountains in Africa. So these extremely tall and very impressive fold belts are formed by continental collision in plate tectonics theory. Now, the next process to talk about is called subduction. Subduction occurs when one plate, usually an oceanic plate, is shoved against another plate, usually a continental plate, and the oceanic plate then dips or subducts beneath the less dense continental plate. So the continental plate is not one to sink into the mantle. It's a less dense rock, right, to 2.7 grams per cubic centimeter. The denser oceanic plate then tends to be the one that dives and subducts into the mantle beneath the continental plate. This is called subduction. Now, as the subducting plate descends into the hot mantle, remember the interior of the Earth, it's really hot down there, right? There's a reason why lava is hot and molten rock is molten. So the subducting plate begins to melt. The process is a little more complicated than that. It also causes the mantle to melt, but for now, we'll just simplify it here. The subducting plate melts, and that molten material then rises through the crust. It's hotter and therefore less dense than the surrounding material, and so that causes it to rise, just like hot air inflates a hot air balloon. And so that molten material then works its way through the crust, and if it can break out of the crust, it forms volcanoes. So the subducting portion of the plate, however, that weight, right, that sinking oceanic plate going into the mantle, that pulling force is actually pulling the remainder of the plate towards the continent and continues the process. So we can see this illustration here. Lithosphere, it's another term for the crust of the Earth. And notice how as it dips beneath the continent, we have molten material coming off of that and forming a volcanic arc just inland of the subduction zone, or you can see that trench there on the seaward side of the subduction zone. So there'll be a trench where the ocean crust is literally going beneath the continent, and these are trenches you can see. You can look at them on satellite. They've been explored under the ocean, and this is the typical way that a subduction zone will work. This animation here helps visualize the process another way. So again, you see the ocean plate, it's diving. You got that trench where it dives beneath the continental plate. There's the continental shelf. And then you can see the molten material rising and forming these subduction zone volcanic chains just inland on the landward side of a subduction zone. And so this is the process that drives many of the world's most active volcanoes. Now, when we think of volcanoes, we like to think of lava, many of us. Lava is cool, it's scary, it's fire, and so forth. And so we get excited about that sort of thing. And often when we think of lava, we're thinking of the runny red molten rock coursing through across the surface of the Earth. We think of lava flows in Hawaii and so forth. Now, when we think of this sort of lava, we're typically thinking of basaltic lava, basalt lava. Basalt lava has a very low viscosity because it has very little silica compared to most other kinds of lava, silica being the dominant mineral in most of the Earth's rocks. Basalt has typically less than 50% silica. This means that the basaltic lava is fairly mild, calm, if you will. It doesn't tend to explode. And that's important for getting a beautiful lava river like we see here and many of the lava flows that you see in Hawaii. These volcanoes, while they can be quite active and they can throw lava quite a ways, the lava itself is fairly predictable and forms these nice lava rivers and so forth. And it leaves this kind of stringy black rock that we see in the Hawaiian Islands. So basalt lava, that's closest to what the mantle is like when molten material comes from the mantle and erupts. It erupts in the form of basalt, most typically. However, the kind of lava that we're going to talk about now is called andesite. Now, andesite occurs when basalt lava partially melts, and that molten material has a different mineral composition than basalt, and it forms a type of lava that's called andesite. And there's other types of lava that are related to this, but to keep it simple, we'll talk about andesite. Andesite has a higher silica content. Higher silica content in lava means it's much more explosive. And so andesite lava doesn't make the cool lava rivers. It just tends to blow up when it's exposed to the atmosphere and to normal pressure. This type of lava, however, is very important. It forms the subduction zone volcanoes we've been talking about. So, for example, we can look at the Andes Mountains, the Andes volcanic chain. Andesite is named for the Andes Mountains. These mountains are formed off of a subduction zone on the west coast of South America. In addition to the Andes Mountains, we have the Cascade Volcanoes, which are also subduction zone volcanoes. They're dominantly andesite as well as dacite and other types of lava, but they are a higher silica content lava because they're also being formed through this melt process off of a subduction zone, just some miles inland, a few 100 miles or so inland of the subduction zone. The subduction zones then form the dominant volcanic regions, volcanic zones of the world. And so the Pacific Ring of Fire is a good example. We've got subduction zones happening all around the edges of the Pacific plate. And these subduction zones drive volcanoes and earthquakes. This is a map of all the Earth's earthquakes plotted from 1900 through 2013. And you can see right away, there's a massive preponderance of earthquakes along the plate boundaries, and in particular, the subduction zones. Every time the subducting plate moves just a few inches, a few feet, that's an earthquake. That's going to create shock waves. That's going to generate tsunamis. These plate motions are not constant. They're not smooth. They're not continuous. The plates get caught up. It's rock after all, and so it grinds against itself and it gets hung up, and then eventually the pressure releases and it moves a little bit, and you've got an earthquake. And so these subduction zones form, as I said, these volcanic chains like the Cascades we see here mapped across the northwest North America, and then along the western coast of South America as well. We have these subduction zone volcanic chains. So that's subduction. The other process to learn about with plate tectonics, and really the corresponding process for subduction, is called seafloor spreading. Seafloor spreading works because as subducting ocean plates are sinking into the mantle, they're pulling the rest of the ocean plate with it, and whatever continents are attached to them, islands and so forth. Everything is being pulled along as like a conveyor belt heading down towards the subduction zone. And that means that the ocean plate at some point on the other side is being pulled apart, right? Because the Earth's surface area is going to remain constant. And so if something is disappearing into the mantle, then you're going to be pulling it apart somewhere else. And those cracks or rifts in the crust are then filled with molten rock from the mantle, which then hardens and cools to form new ocean floor. This essentially means that the oceans are growing. Even as the ocean plates are subducting into the mantle, the ocean plate is growing at some point, usually somewhere in the middle, a mid-ocean ridge. We'll talk about that in a minute. And so the ocean basins actually tend to expand. So seafloor spreading plus subduction keeps the Earth's crust area constant. We can see here an outline of the ocean ridges. Notice the mid-Atlantic ridge there, and notice how nicely it matches the shapes of both South America and Africa. That's because the mid-ocean ridge is where Africa and South America separated. And then as the Atlantic Ocean basin grows and material is coming up, and as it comes up, it pushes to either side. So it's going to push a little bit towards Africa, and the other side is going to push towards South America. And so the continents move apart along a line that matches the shape of the continent. You can really see the whole puzzle taking place there. Notice the Pacific mid-ocean ridge actually runs really close to the western border of North America. And that's an important reason for a lot of the interesting volcanic activity and earthquakes in the Cascadia region. So here's an animation of a mid-ocean ridge. So again, remember that the material comes up and it's spreading in both directions. So the ocean plate is growing to both sides of the mid-ocean ridge. And notice that the mid-ocean ridge itself, it's a ridge line. It's a topographical high point in the on the seafloor, because that molten material is less dense than the colder material, right? Because molten rock takes up more space than when it cools and becomes hard. And so there's a high point where the molten material is coming up. And as you move away from the ocean ridge, the oceans actually get a little bit deeper as you go down that ridge line. And so this forms essentially a mountain chain, as well as a lot of volcanic vents and other interesting hydrothermal activity in these mid-ocean ridges. So now we can put seafloor spreading together with subduction, and we can get a look at how South America broke away from Africa. So we're looking at South America here on the left and Africa on the right. And this animation, as it plays, pay attention to what happens along that crack where these two continents begin to separate. So there is that mid-Atlantic ridge line that opening up, the seafloor spreading is occurring. It's pushing the continents apart, even as subduction on the Pacific side, on the South American side, is also causing South America to move in that direction. I'll play that one again for you. It's a good animation here. The numbers there in the upper right, those are dates, I believe, 120 million years ago, 60 million years ago. Again, we're just talking conventional plate tectonics, secular model. This is how it works. The other thing we'll mention, this mostly just as it's a popular example of plate tectonics, and it's kind of a fun one. We won't talk too much about it, but volcanic hotspots. The Hawaiian Islands are a common example of these. So the Hawaiian Islands, of course, are a chain of volcanoes, and the reason why it's a chain of volcanoes is because there is a hotspot underneath Hawaii. And that hotspot is a place where molten material is coming up through the mantle, and it's erupting through the ocean crust. And as it erupts, it spills out lava, and that lava cools, it hardens in the ocean, in the seawater, and produces these volcanic islands. Now, as the Pacific plate moves over the hotspot stays more or less constant in the same spot in the mantle, but the ocean crust is moving across it. So as we can see in this animation, we have the lithosphere plate that's just referring to the ocean crust, the Pacific plate. We've got a hot spot forming the volcano, and now the plate moves, and new volcanoes are formed over the hotspot. And so this creates these volcanic chains. And these are really interesting. You can look at them on satellite maps. You can see where subduction or where plate motion has changed, and you'll see these kind of curves or sharp angles in the island chain. So hotspots are very interesting. So plate tectonics, in summary, it's a global model for geology and Earth history. And that it's important because what it is it's a big picture theory. It doesn't answer every question you could have about geology, but it puts all those questions into a framework that makes them easier to think about and easier to hopefully answer. So it's a very powerful theory in that way. Plate tectonics proposes that the Earth's continents were once together, broke apart, and moved to their current positions. I'm simplifying it a little bit because continents can break apart, come back together, and break apart again, it turns out. But plate tectonics explains a lot of evidence. Geology, we talked about paleontology, the fossil records between different continents, biogeography, where animals and plants are, where they live and how they got to where they are around the world, geomagnetism, climate, so many things are tied to plate tectonics. It's an extremely successful theory. It's been confirmed by many predictions, many lines of evidence, and it's one of the most successful theories in scientific history. But there's a problem, folks. because it turns out the plate tectonics poses some puzzles for those of us who accept the Bible's account of history. The biggest one is that plate tectonics is slow. It operates at very gradual rates today. Plates move a few centimeters per year. A vast plate like India moves 12, 15 centimeters in a year. That's blazing fast if you're a continent today. It would take over 100 million years just to get the plates to their current position, if we assume that they are all together in the supercontinent that we were looking at earlier on. So at today's rates, subduction and plate collision would require hundreds of thousands to millions of years to form the volcanoes, the volcanic islands, the mountain ranges that we see around the world. So plate tectonics at today's rates is not compatible with the biblical history or the account of the flood. So should I leave you there? Of course not. Let's look at the Bible. We already saw in Genesis chapter 1 that during creation week, God says, let the waters be gathered to one place, let the dry land appear. So we know that the idea of a supercontinent and a single ocean, a global, one ocean and one continent, that is clearly not incompatible with Scripture. In fact, the Bible seems to suggest it. And in fact, we think about a lot of the aspects of plate tectonics that we talked about, subduction, seafloor spreading. There's nothing obviously unbiblical about those things, but the time scale required is certainly a problem. But this is where things get interesting when we look more closely at the account of the flood. Genesis chapter 7, verse 11. In the 600th year of Noah's life, in the second month, on the 17th day of the month, on this day, all the fountains of the great deep split open, and the floodgates of the sky were opened. Now that phrase, the fountains of the great deep split open, that's a poetic expression, but the great deep in the Hebrew Bible always refers to the ocean. So the fountains of the ocean being broken open, this suggests something is happening on the seafloor of the great deep that's breaking something, breaking open a fountain of some kind. And then the floodgates of the sky, or the windows of heaven, many translations will say, they were opened secondarily. We like to think of that as rain, but technically the Bible talks about rain later on in the flood account. It doesn't really tell us what these windows of heaven refer to. So these biblical hints, they're clues, and creation scientists who are interested in what to do with the seeming power of the plate tectonics theory, but the challenges that it poses to the challenges that it poses to the Bible's account of the flood and of Earth history. They took note of these things, and a group of creationists, physicists and geologists in the late 80s and early 90s, they took these things together and they produced a new theory, a new version, a new flavor, if you will, of plate tectonics theory, taking this data from Scripture and taking the time constraints of the Bible and of the flood and applying that to plate tectonics. And they produced a new theory that we're going to talk about now. This was first published in 1994 at the Third International Conference on Creationism. And the primary researcher, or one of the primary researchers for this new theory, is Dr. John Baumgartner, a geophysicist with a long and illustrious career as a physicist and as a computer scientist as well. Dr. Baumgartner produced a computer model to test their theory and to test some of the ideas that they were proposing. Their theory came to be known as Catastrophic Plate Tectonics, a global flood model of Earth history, the title of their first paper. And what was very interesting about this model is that catastrophic plate tectonics, according to the researchers, appears capable of explaining a wide variety of data, including biblical and geologic data, which the slow tectonics theories are incapable of explaining. In other words, their new theory explained everything that conventional plate tectonics theory explained, but it could explain more evidence, both geologic evidence as well as the biblical evidence, that conventional slow plate tectonics simply doesn't explain at all. So this was very exciting. This is an example of a creationist theory that was created really by taking the best of what was available from the secular conventional paradigm and model, combining it with the Bible's the biblical evidence, the biblical data of Earth history, and putting those two together and seeing what came out. And what came out is this new theory of catastrophic plate tectonics. So how does this work? Well, when you get into catastrophic plate tectonics, what you find is that for the most part, you're talking about the same processes. You have seafloor spreading, you have subduction, you have hotspots. The difference, however, is at the rate that these things take place. And the most important one is this process called runaway subduction. Now, we've already talked about subduction and the ocean plate diving into the mantle. However, at present rates, this is a very slow dive. Again, we're talking centimeters per year. However, Dr. Baumgartner in his computer modeling was able to show that the physics of the mantle and of the Earth's crust could be placed into a condition where subduction could begin and proceed extremely rapidly in such a way that it actually creates a runaway effect. And I'm just simplifying this to hopefully get the point across. But the idea with runaway is that the process of subducting, so as the crust, the ocean crust dives into the mantle, it actually deforms the mantle in such a way that the mantle heats up and becomes more deformable. It becomes softer. It becomes more. It becomes less resistant. This causes the subducting plate to drop even faster, which heats up the mantle and deforms it even more. And the process repeats in a feedback loop where it's essentially feeding off of itself and going faster and faster and faster, to the point where instead of talking about ocean plates subducting at centimeters per year, we're now talking about meters per second of plate motion, oceanic crust diving into the mantle at meters per second, a conveyor belt that you could, if you were looking at it, you would die. But if you could look at it from a safe vantage point, you would be able to watch the ocean floor just flowing into these subduction zones and diving through the mantle at incredible rates, 3 billion times faster than we see them today. And this process, as far as the geophysics is concerned, is entirely plausible. And in fact, there's good evidence that this, in fact, did happen, which we'll talk about. So this is a couple of snapshots from the computer model. We can watch that blue material is the subducting ocean crust diving all the way down to the base of the mantle. And notice that time indicator there on the top. Here's 1 day into the simulation. 5 days into the simulation, we're halfway through the mantle. 10 days, we're just about to the bottom. And by 30 days, the ocean crust has dived completely through the mantle and struck the core mantle boundary, which you can't really go through that boundary, and is now piling up cold ocean floor material at the bottom. I say cold because that blue color there is indicating the relative temperature. And hold on to that, because that's important, right? It's only been 30 days for this particular subduction zone, the simulation. It took 30 days for that subducting ocean crust to reach the bottom of the mantle. Now, this runaway subduction pulls the continents apart in just the same way that conventional plate tectonic subduction does. And so the continents are pulled apart following these subduction zones. They're being pulled apart because the plates that they're attached to are themselves being subducted. And this causes the continents to move. And most importantly, for this simulation, Dr. Baumgartner was able to show that runaway subduction does in fact move the continents, and it moves them in the right location. This is a computer generated graphic. It's a little difficult to read, but the dark outlines here in the center of the frame, we're looking at Africa and South America. Notice that they're kind of hugging each other. If you look off to the left side of the picture, there's a fainter line which indicates the present location of South America. And the important thing to notice is that the arrows are showing the direction that that piece of crust is moving. And notice that Africa is moving to the north and west and kind of curving a little bit. And South America, on the other hand, is going away from Africa and to the west towards its present location. And there's a lot of really cool things about this simulation. This is actually extremely advanced software that Dr. Baumgartner produced. That was one of the first software packages that could accurately model the way the mantle works, the way the Earth's crust behaves and operates. And he wrote it essentially for the purpose of trying to simulate the global flood and catastrophic plate tectonics. And his program has been very successful. It's known as the Terra computational mesh. And it's still being developed today, in fact. There are other programs now. The science has advanced quite a ways, but nonetheless, this was a very important computer program, and it was able to accurately predict and accurately simulate the way that the Earth behaves in a catastrophic plate tectonics scenario. So rapid plate motion means rapid and runaway subduction. So rapid plate motion and runaway subduction mean rapid seafloor spreading. So rapid, in fact, that you'd be ripping apart ocean basins or continents, and as ocean waters flooded in to these rift zones, they would open up and essentially expose hot mantle material directly to cold seawater, cold ocean water, rather than the nice, slow, steady pace of the mid-ocean ridges today. This would have been far more dramatic, far more sudden. And in fact, computer modeling has indicated that this phenomenon would lead to essentially a chain of the biggest geysers ever generated on Earth. In fact, it would have led to supersonic steam jets, which would have been sending ocean water skyrocketing into the atmosphere up to maybe 60,000 feet, according to some calculations. So this process here is a possible explanation for what the Bible calls the windows of heaven, which again, the windows of heaven is not necessarily rain, although it does seem to result in global rain. And these supersonic steam jets that would have been created by rapid seafloor spreading would indeed have created a global torrent of rain that was essentially ocean water being ejected into the upper atmosphere and then condensing and falling all over the Earth. And so right there, we can see an explanation for the fountains of the Great Deep breaking open. That would be these rift zones, these continents and plates pulling apart in the deep ocean. So this could be the breaking up of the fountains of the Great Deep. And then these steam jets could be an explanation for the windows of heaven or the floodgates of the sky being open. So that's great, but we don't have a global flood yet, right? We've got things moving very fast. We've got monstrous earthquakes. Remember, we said that a few inches of movement in an instant that can generate an earthquake that could level a city. Potentially, it can generate tsunamis. Now we're talking about the continents moving at meters per second. We are talking about hours and days and weeks of unearthly earthquakes. And in fact, we have geologic evidence of these earthquakes, which we don't have time to talk about. But how do we get a global flood? We're going to get tsunamis. We're going to get earthquakes. We got steam jets. We've got volcanoes going off. What else is going on that would give us the conditions we need for a global flood? Well, remember, we talked about how the denser ocean crust rides lower in the mantle and gives us the ocean basins that mostly keep the ocean water where it belongs. Well, what happens when that cold basalt ocean crust subducts and it's replaced by hot molten mantle material? That hot molten basalt from the mantle is actually going to occupy more space. It's going to take up more space than the cold basalt would have taken. And that means the ocean floor, the sea floor, is going to rise with respect to the continents. And so this means that as the ocean floors are being subducted, they're being torn away, they're subducting to the mantle through runaway subduction. The upwelling of mantle material to replace the missing ocean floor is in fact going to lift the oceans. In addition to creating these steam jets, it's going to actually displace ocean water and spill it over the continents. And you've got a global flood. And so this full circle of processes, runaway subduction, rapid seafloor spreading, gives us the conditions necessary to get the ocean water out of the ocean basins and over the continents in the way that the Bible seems to describe. So catastrophic plate tectonics essentially speeds up continental motion by 3 billion times. We're talking from centimeters in a year to meters a second, a brisk walking pace. That is lightning fast when you're talking about rock. Runaway subduction, rapidly subducting plates heat up the surrounding mantle material. This causes the mantle to deform more easily, which speeds up subduction even further, and you have a runaway effect. And this runaway effect will continue until all of the old cold ocean floor is subducted. Once it's all subducted, the process will come to a stop. The cold ocean floor that's being subducted, I say cold as opposed to the hot material that's replacing it, the cooler material is essentially the fuel for the runaway subduction process. And once it is subducted, the process will grind to a halt. Now, computer modeling demonstrates that runaway subduction does in fact work, and it does in fact move the continents at meters per second. And this compresses the time needed for plate tectonics into the 1 year long Genesis flood as well as the post-flood period. So catastrophic plate tectonics, like the conventional theory, has been very successful. It can explain much data, much evidence that conventional plate tectonics struggles to explain. It can explain, for example, the necessary energy needed for building mountain chains like the Himalayas. We've talked about that already. We'll talk about it in a moment here. Runaway subduction also predicts that subductive plates would penetrate the entire mantle. Now, we didn't talk about this earlier, but with subduction, as conventionally understood, moving at centimeters per year, subducting plates can only get so deep into the mantle before they get to a depth where the pressure is so high, they can't actually sink any farther. It's about 600 to 700 kilometers beneath the surface is the zone where subduction is supposed to stop. But with runaway subduction, the plates are moving so quickly, they are able to penetrate that boundary and in fact, make it all the way to the bottom of the mantle at the core mantle, the boundary between the Earth's core and mantle. CPT also predicted that subductive plates, these ocean floors, could still survive. They might still exist, rather, at the bottom of the mantle as cold material. Cold, relatively speaking, they would be cooler than the surrounding mantle around them. And then lastly, we'll just mention that CPT, along with creationist models of the magnetic field of the Earth, predicted that rapid geomagnetic reversals would be discovered. We're not going to go into that. That's a whole other talk. The point is that all of these things have been confirmed independently through geologic research. We'll talk a little bit about, just really briefly, about a few of these. So how fast do you suppose the red car was moving? Centimeters per year sound about right to end up underneath that gray car there. Here's a better example. So we think this might have been a slow motion incident. Someone just left the parking brake off and eased their way beneath the SUV. Or how about this one? Was this guy just idling and the car just kind of made its way up onto the roof? No, you don't get these sorts of uplift and collision scenarios unless you have a lot of energy. Because otherwise there are other processes that the car, it's going to nose its way into the house, and it's going to crumple the bumper, and the tires are going to spin, and that's going to be about the end of it. You need to have a surplus of energy, And in order to get these spectacular situations, like a car on a roof or a seafloor 14,000 feet in the sky, in the case of a mountain fold belt. So when we're talking about continental collision, there's real questions about if India, for example, collides with Asia at the blistering rate of 12 centimeters a year, how is that going to raise Mount Everest and the rest of the Himalayan mountain chains? Wouldn't erosion by itself be enough to keep up with a few centimeters every year? You can erode a lot more material than that just in a good flash flood. And so it's really difficult to see how those present rates are going to get the Earth's uplift mountain fold belts at the elevations that we see them today. So continental collision seems to require a lot of energy. And there's other evidence of this as well we don't have time to go into. We see folds in these mountains that seem clearly to have happened while the material was still soft and deformable. That can't be explained with slow uplift. This takes rapid shockwave style uplift, which is what would have happened in catastrophic plate tectonics. You would have seen the Himalayas just jolting their way up into the sky, folding and twisting and so forth. And that's a feature that is very explainable in catastrophic plate tectonics, but is not nearly as straightforward in conventional plate tectonics. Now, some of the more exciting examples, however, of the success of CPT would be the prediction, really, of cold material. And again, cold, relatively speaking, the CPT predicts, because according to CPT, of course, according to the creationist interpretation, this runaway subduction would have occurred only a few thousand years ago. And a few thousand years is not enough time for those ocean plates, that old seafloor, to entirely melt. It's hot down there in the mantle, but that's a lot of rock that was pretty cold when it went in, and it's going to take time to assimilate into the mantle. And so in a young Earth scenario, that material should still be around. And indeed, through a technique called seismic tomography, which was not around in 1994 when they proposed CPT, these pictures here are from a secular journal, and these are images, reconstructions, or representations similar to how an ultrasound would work using seismic waves. We can actually see that cold material. In fact, we've got better illustrations of it now. This is from a more recent paper. We can see that folded up pile of cold ocean crust just sitting there at the base of the mantle. If it's been there for millions of years, it should have had plenty of time to assimilate. So the fact that there's still cold material from the old ocean floor piled up at the base of the mantle is incredible. And it's an incredible confirmation of the CPT theory, even though, of course, it was completely ignored in the scientific community. Similarly, CPT and runaway subduction predicts that there would be mantle-wide subduction. What that means is that subduction is going so fast that it penetrates the entire mantle and it makes it to that mantle core boundary at the bottom there. That was not supposed to happen in conventional plate tectonics, and yet it indeed does happen, and it is now, it's been detected, and it's a recognized feature of plate tectonics. CPT predicted it, conventional plate tectonics did not. So to summarize CPT, catastrophic plate tectonics is a creationist catastrophist model for global tectonics. Like plate tectonics in the conventional sense, it's a framework model. It doesn't answer every question, but it gives you a framework, a place to put all the puzzle pieces together, and it helps you kind of organize your geologic puzzles and questions into a structure that is a little bit more manageable. At its simplest, it's plate tectonics on hyperdrive, on fast forward. It's truly a productive scientific model. Granted, it doesn't have nearly the number of scientists using it, right? So plate tectonics, you've got tens of thousands of scientists, maybe more, that are using it and developing it and refining it. CPT might have a few dozen scientists, maybe 100, doing the same. And so it's in its infancy in comparison, and yet it's been able to make many successful predictions, and it continues to guide research. It continues to help creationists ask better questions and do good science as a result. Runaway subduction provides the energy needed to rapidly resurface the Earth during the flood. Runaway subduction is the engine of CPT. It's what drives the entire process. And when runaway subduction comes to an end, because all of the subducted material is gone, that brings the process to a halt, and it's never going to repeat. You can't reproduce those conditions again. CPT, of course, rejects the assumptions of uniformitarianism. The past was not like the present. So again, many similarities: subduction, runaway subduction, seafloor spreading in plate tectonics, rapid seafloor spreading in catastrophic plate tectonics. The theories are very similar in many respects, but the additional energy levels involved in CPT give it a lot more explanatory power. It allows it to explain a lot of data. And I didn't touch on any of a dozen examples I could have easily given of things that CPT can explain that plate tectonics just doesn't offer an explanation. People still, they know they're there. It's not that it's controversial that these evidences exist. It's just plate tectonics isn't the explanation. Well, CPT offers to be that explanation. So it gives us a lot of explanatory power, and that's what you want in a good scientific model. As I said earlier, it's a catastrophist model. It rejects gradualism, and in fact, that really is the key distinguishing factor between plate tectonics and CPT, is the rejection of gradualism and uniformitarianism. Now, CPT is not perfect. I'll say that right away. The model is still being critiqued and refined by creationists. Of course, it's also been critiqued by secular geologists, although I would argue not very fairly. So CPT, it's got puzzles, it's got problems. It's not a perfect model. No model, creationist or otherwise, is perfect. Every theory, every model has things that are difficult to explain. But CPT does give creationists a very powerful tool for understanding the geology of the past as well as the present. So with that in mind, let's just take a few more minutes to go over kind of an application of plate tectonics and CPT indirectly as we move towards our eventual goal of Mount St. Helens in 1980. We talked about plate subduction quite a bit. Oceanic crust diving beneath continental crust. There's partial melt. The melt ascends through the Earth's crust and erupts as a volcanic arc within the on the landward side of a subduction zone, as we see here. You can think of this as being the Pacific Ocean and the northwest of the United States, and you will be right where we want to look, at the Cascade Volcanoes. So the Cascade Volcanoes dominate the western coast of North America, from Canada down into California, and it's part of the Ring of Fire, as you mentioned earlier. And these volcanoes are very much the kind of classic volcanic mountain form, their figure, right? The mostly conical, gray, snow-capped mountains. Of course, we have exceptions like Crater Lake, Mount Mazama. Crater Lake is a volcano that essentially blew out its own magma chamber, and so ended up with a big vacant hole beneath the mountain. And that hole was not strong enough to hold the mountain, and it literally collapsed into the ground. It's quite an eruption. The summit went from 12,000 feet to well, much less than that, as we can see here. The Three Sisters in Oregon are part of the Cascade of volcanic chain. Mount Baker, Mount Hood, These are all very beautiful volcanoes, very beautiful mountains. Of course, a very beautiful part of the world. Mount Adams, Mount Shasta down in California, and then Mount Rainier is the tallest of the Cascade volcanoes with a summit elevation of 14,400 feet. Mount St. Helens, of course, used to look like one of those. It looks different today, but it was also a nearly 10,000 feet tall, very pleasing volcanic cone, beautiful snowcap. Remember, these are subduction zone volcanoes, and so they're formed primarily of andesite and similar lavas, dacite, and so forth. And that produces, that's the gray color. That's the color of that type of rock. And the important thing about these andesite lavas is that they are not as runny as basalt, right? Basalt just tends to form lava rivers and flows away. You can't really build a mountain out of that sort of lava. So andesitic lava is thicker, and so it tends to pile up. It's explosive, but it's not so explosive that it blows away the mountain. Like, for example, rhyolite lava that you get at supervolcanoes. We'll talk about that in a minute. So as a result, andesitic lava from subduction zone volcanoes is so again, andesitic lava from subduction zone volcanoes is well suited to build up this, what's called a stratovolcano cone. Strato refers to the layers. So each eruption produces another layer of lava and ash and other volcanic material that's ejected from the central vent. We can see the magma chamber there, and the throat of the volcano there in the center. And then, of course, there will be other volcanic vents, dikes, and so forth that will come off of the main central vent of the volcano. Volcanoes can be very complex systems. It's not just a cone with a crater, but that's a pretty typical cross-section there that we're looking at. So stratovolcanoes are not the only volcano type. We also have shield volcanoes. This is more akin to what you see in the volcanic islands of Hawaii, for example. Basalt lava doesn't form very tall mountains. It runs away and flows off and spreads out over a wide area. Nonetheless, you can see the magma chamber, the central vent, and so forth. And so it is a similar type of process, but a different type of lava, and so a different expression, different shape. The other type of volcanoes that we like to talk about are supervolcanoes. And the Yellowstone Caldera, Yellowstone Volcano, is one of the most famous examples of that. Here you can see in the top left, the yellow streak there is the ash accumulation from Mount St. Helens in 1980. And you can see how it's dwarfed in comparison to these Yellowstone eruptions that have occurred from that particular supervolcano. The Yellowstone Caldera, in fact, is so large, you really can't see it in any one frame. In this map here, you can see that red outline, which shows the general area that the caldera is believed to occupy. Now, these caldera supervolcano eruptions are enormous, as I said. But what's very interesting about all of these large volcanic eruptions, these supervolcanoes, is that there is a very distinct pattern as we go back in time, back through history. The farther back we go, the larger the eruptions seem to be. We don't see supervolcanoes in the very recent past. We see them going back conventionally 45, 50, 65 million years and so forth. But even in a biblical time scale, these supervolcanoes seem to have been going off in quick succession shortly after the disturbance, the upheaval of the Genesis flood. And this is an important point to remember. Sometimes you will hear in the media about the Yellowstone volcano and that it's overdue for another big eruption. And geologists are being asked questions about when is it going to blow? Well, I'm not going to come out and just predict anything about Yellowstone, but keep in mind, when we say Yellowstone is overdue for an eruption, well, we're presupposing millions of years of Earth history where Yellowstone has erupted every, 10 million years or so. It's erupted over the past 20 to 40, 50 million years. a number of times, and there's been long periods of quiet in between. And when you look at it from that perspective, then you could say, oh, well, it's been a long period of quiet. Maybe we're due for another super volcano at Yellowstone. But if we look at it in the biblical time frame, all of those eruptions are compressed into one very short, very active a period of volcanic activity right after the flood. And in fact, it seems like much of the volcanic and tectonic activity that that we see in the Earth's in the rock record seems to represent a exponential decline of volcanic intensity, of volcanic output. We can see here the example of the comparison of the volume of ash put out by these large eruptions in history, and see Mount St. Helens is that little red pixel by comparison. Oh, I'll cut that. And so as we look at these eruptions of the past, we see a pattern, we see a steep decline in power and intensity. And that is consistent, I believe, with the biblical record of a massive worldwide upheaval at the time of the flood, an upheaval that was tectonic and volcanic in nature. And then the Earth has been settling down ever since that high point. We can also see this in other areas when we look at climate and we look at sea levels and so forth. There seems to be a peak and an exponential decline to the present. So Yellowstone, by that measure, is maybe dormant, maybe even dead volcanically. There's certainly no reason, looking at its past eruptive history, to suppose that it's overdue for another eruption in a young Earth time frame. Mount St. Helens in 1980, that's what we're going to talk about next. That's what we're headed towards. One of the most well-studied eruptions, and certainly an awesome display of power, although puny by comparison to the super volcanoes of the past, and certainly compared to the volcanic activity and earthquakes and so forth that would have taken place during catastrophic plate tectonics. Nonetheless, it is an astounding example of God's power and of the forces that are at work within our planet. And we're going to end with this reading from Hebrews chapter 12, verses 25 through 26. See that you do not refuse him who speaks, for if they did not escape who refused him who spoke on earth, much more shall we not escape if we turn away from him who speaks from heaven, whose voice then shook the earth. But now he has promised, saying, yet once more I shake not only the earth, but also heaven. I believe the author of Hebrews here is referring back to the last time God shook the earth, the entire earth, at the time of the flood. The upheaval that took place during the year-long flood in Noah's day was not simply an accident of geology or tectonics. It was an act of judgment by God on man's sin. And there is a future judgment, a future shaking coming, according to the scripture. Hebrews 12, 28 through 29 continues. Therefore, since we are receiving a kingdom which cannot be shaken, let us have grace by which we may serve God acceptably with reverence and godly fear. For our God is a consuming fire. Amen. Thank you for your participation, and thank you for listening to this presentation. Our next talk will be on the eruptions at Mount St. Helens in the 1980s. We'll break down that sequence of events and demystify it, and hopefully learn some interesting things about those eruptions and what clues they might give us about the sort of processes at work during the flood of Noah's day. Thank you.